join us on this snowy night. I'm Diane Hall, current president of the Warren Astronomical Society. Do we have any new members here tonight? Any first-time people? Hi, welcome. How'd you find out about us? That's fantastic. Well, hopefully you'll have a good time. Some of our talks can go a little, bit above his age level, but we're always glad to have people here.
He'll be teaching us.
Yeah, that's true. Okay, so in terms of business going on, if you had a chance to read the WASP this week, I issued a call not just for a treasurer, but for a secretary. So Charlie's got a little address for you all to read tonight in lieu of a normal secretarial report. And we're also looking for a snack captain. The board decided that right now we don't have the capacity to bring snacks, the board themselves, as they've been doing the past year. So we're looking for a new snack captain who's willing to bring the snacks. Or snacks may be sporadic at best. Yes, Jeff.
Are we still reimbursing for snacks?
Yes.
Okay. You don't have to pay to bring.
Yeah, of course. The snacks we're not expecting people to dip into their own pockets for the snacks. We just need somebody logistically to be able to provide the snacks and potentially carry around the bag of dry goods. So, in addition to that, we've got some, excellent. We've got some good news on the Treasury front. Good news on the Treasury front just walked in the door. And we've got an announcement that didn't quite make it into the WASP. There's a member that's interested in selling an Orion XT10. So if anybody's into an Orion XT10, let me know. Otherwise, we'll just put an ad in the WASP for the next go round. Yes, Jeff. No, I can hook you up with him though, because that's a nice telescope. Like that's a telescope to. Yes, Jonathan.
So for those who don't know what that is, right away, it is a reflective telescope, it's 10 inches across. This box breaks down into two pieces, both of which are easily variable. So it's a very large telescope, but it's also very important.
Why did the mirror just die?
Window.
There we go. Sorry about that. Comment from Zoom that we cannot hear what Jonathan said. Jonathan was explaining that the XT10 is a very good beginner telescope that has a 10-inch mirror and fits into most cars these days, I would say. Not if you've got a smart car. Yes, Parker. Okay. All right, so we've got some interest in the XT10. Come see me at the break and I'll hook you up with the gentleman. Okay, Bob, could you repeat what you typed in the chat for the benefit of our young guest?
Oh, hi there. Yeah. If God, take a look at NASA Eyes on the Solar System. It is an app that'll run
Hang on, Bob.
Hang on, Bob. You're the only one who can hear you right now is Diane.
Oh,
Hmm.
testing.
I can hear you perfectly.
No,
Bob.
it's not you. It's
It
me.
needs to come out over the speakers in the audience there.
There we go.
Testing.
Okay,
There you
we got
go.
you sorted out now. Thank you.
Okay, so take a look at NASA Eyes on the Solar System. It is a web app that'll work on desktop, tablet, phone. There's a couple different apps, but the solar system one, you can click on any planet, zoom right into it, see what's orbiting, click on those and zoom into those. It'll bring up a pop-up with links, information on the object you're looking at. It's a very cool app, and you'll curse me because there's a lot of stuff in there, and they keep adding stuff. It'll pop up with 4 things on the left side, latest launches and latest news. It's very cool.
All right, thank you for that, Bob. With that, I'd like to turn things over to the first Vice President, Jonathan Cade, for his report.
Well, our calendar is filling in nicely. I'm going to be putting some requests for presentations for people who, especially for people who have not given presentations before. Some things like a detailed look at the moons of Jupiter. So if you have an idea for a presentation, I would love to hear it. If you don't, please check the list in the WASP. That's it.
Thank you, Jonathan. Over to Riyadh, the Observatory Chair.
Yeah, thank you, Dan. Hello, everyone. Unfortunately, it was cloudy and the weather conditions were pretty bad for this last open house, so we decided to cancel it. However, we have, of course, this month open house. It's on February 28th, and let's hope for clear skies and better weather conditions. So hopefully we'll see everyone out there. Thank you.
Okay, the sound cut out a little bit. Riyadh was announcing that the previous open house was canceled because of bad weather, which we've had a lot of, and that we've got the upcoming open house on the 4th Saturday of February. So like normal. Thank you, Riyadh. Anything else?
Maybe we can add just one more thing. What we used to do in the spring is we would invite some people out.
Your sound is cutting out, Riyadh.
I'm sorry about that. I guess we just need to, can you hear me now a little bit better?
Yes.
Okay.
Yes.
All right. So in the spring, we used to have a day out, one of the open houses for cleanup a little bit. So if anybody's interested, this year, I'd like to have it on the open house for April. So if you can come on out there, we'll have an open house as well as bring a couple of maybe bags with you, trash bags, some maybe a broom or two. We have a vacuum there as well, and we'll try to clean up the place a little bit. That's it. Thank you.
All right, so Riyadh was trying to say that we've got a cleanup day scheduled for the April open house, so that would be the 4th Saturday in April up at Stargate. So if you are interested in keeping Stargate looking nice, show up with a couple of trash bags and we go to work. Volunteers happily accepted. Okay, with that, let's go to Secretary Charles. He's got something to read to you tonight.
Good evening, I'm Charlie Strackbine, and dear WAS membership, I want to take a moment to say thank you. Serving this organization has truly been a joy. It has been an honor to contribute, to learn, and grow alongside such a thoughtful and passionate group of people. I've gained more knowledge and perspective than I ever expected, and I'm genuinely grateful for the opportunity to have served. As I step back into a role of participating member, I do so with a full heart and deep appreciation for this community. I look forward to continuing to learn, observe, and enjoy astronomy together, especially our first Monday meetings at Cranbrook and our third Thursday meetings at Macomb. Both have always been not only educational, but welcoming, engaging, and a lot of fun. Thank you for the trust, the camaraderie, and the shared curiosity that make this group so special. I am thankful for the experience and excited to remain a part of it. With sincere gratitude, thank you, everybody.
Thank you, Charlie. We're sorry to see you go from the board, and we're glad that you're staying around the club. All right, treasurer, David Baranski has thankfully stayed in the role for a little bit longer than his actual term, but as of tonight, we do have a new treasurer candidate who steps forward and just needs to be formally appointed by the board in a proper motion. Would the new treasurer stand? is very familiar to you all. Thank you, Dr. Dale. I know it's quite a role, and glad to have you with us. All right. Yes. Outreach. Yeah.
That's me.
That is.
Tina did my homework for me. You're not getting it. I got Night Sky Network outreach pins. I ordered 10 of them. I need to go through the 2025 outreach to see who my 10 biggest participants were. And then I'll be distributing those. Hopefully, maybe the next Cranbrook meeting is a good time to do it. And if they don't come to Cranbrook, they'll get it at Macomb. In past news, Dale Parton spoke to the Seven Ponds Club on the 17th. These are not where my notes are. About the creation of the elements, yes? Origin of the elements, I believe was the talk. And then the Cranbrook event was canceled because it's been so darn cold. Warm out tonight. Oh my gosh, so warm. Almost above freezing. They've rescheduled for the 20th of this month. It's a Friday. I think the same crew is probably
Jupiter, February.
rolls off the tongue. That's it for outreach. I don't think I had anything else.
If anyone is in the Belleville or Ann Arbor area, we do have a public outreach event at the Belleville Public Library coming up on the Thursday before the Cranbrook event. So you have 2 events to choose from that week.
Are they doing telescopes or
Yeah,
something?
telescopes.
That's on my.
I only need like 2 people.
Okay. And sorry, as usual, if you're interested at all in helping out with outreach, you can talk to me. You can email info or the board or any of the web addresses. I'll find you, or you can talk to Tina and she'll talk to me.
All right, so that brings us to publications.
Oh, one last thing. Sorry, I usually do my little history thing. The Cranbrook event on the 20th is the anniversary of Friendship 7. John Glenn. All right.
That's cool. Publications.
Can you guys hear me?
Yes, we can hear you now.
Okay. I got nothing. Newsletter is online.
That's
all I
not
have.
nothing. That's good. WASP being out on time is always good. As you, of course, you're always taking ideas for columns, commentary, etc., right? Just send it along to publications@warrenaster.org. Okay. One thing that I would like to see this year is reviving some of our special interest groups that have fallen by the wayside. Of course, we used to have a solar group led by Marty Coons, the late great Marty Coons. We had a radio group. Now that's in the process of a formal revival. We still have the Double Star group. We had other subgroups come and go. If you have a particular passion, simply let us know. Let the board know, and we can appoint you the subgroup captain, and you can do your thing. Be it, a different sort of astronomy. We used to have a urban observing subgroup for people who would do the best they could with the public and light polluted skies, and of course, back in the day, we had the discussion group. So if you are interested, let us know. We would love to revive as many of these subgroups as possible to offer our public as diverse a slate of activities as possible. And with that, I'll pass the baton to, yes, astrophotography. Yep. That's a good one. Yeah, we do have kind of a group. Pass the baton back to Riyadh for the Double Star group.
Yeah, actually, if we get a chance, come February, open house, we will look at the constellation of Orion. There are lots of double stars in Orion, as well as Canis Major. We should be able to have a lot of fun looking for very tight doubles.
That sounds good. Gotta love the dog star. Okay, radio astronomy.
This is not the formal presentation.
Yeah, just the radio astronomy update.
Oh, okay. Yeah, I'm Tom Hagan. I like radio, I like astronomy. And I volunteered to be the coordinator for the radio astronomy special interest group. Anybody interested? Yeah, I've got a 15-minute presentation on Jupiter radio emissions. It's kind of fun, I hope, for everybody.
That sounds great. We've had a member reach out to us online that I need to hook you up with. They're interested in doing radio things. They weren't able to make it tonight, but so. Okay, any other subgroup captains present that want to give a report? All right, with that, I believe we've got special guest David Levy on the line. Have you got some words for us, sir?
Yes, I do. Thank you so much. And I'd like to add my welcome. I was going to give you a quotation from John Milton today out of Paradise Lost, where he wrote, "Hereafter, when they come to model heaven."
Sorry,
Right?
sorry,
stuff-
David, we have some audio issues.
Can you hear me at all?
We have a loose cable.
Try it again.
Try again.
Okay, so I was going to quote from Milton from Paradise Lost. Can you hear me better now?
Yes.
Okay, and he writes and calculates the stars, and this is out of Paradise Lost, how they will wield our mighty frame, how build, unbuild, contrive to save appearances, how gird the sphere with centric and eccentric scribbled o'er, cycle and epicycle, orb and orb, the last line being quite famous. But I found something that I thought was even better. It's from out of Walden, published in 1854 by Henry David Thoreau, my favorite author after Shakespeare. Both place and time were changed, and I dwelt nearer to those parts of the universe and to those eras in history which had most attracted me. Where I lived was as far off as many a region viewed nightly by astronomers. We are wont to imagine rare and delectable places in some remote and more celestial corner of the system, behind the constellation of Cassiopeia's chair, far from noise and disturbance. I discovered that my house actually had its site in such a withdrawn but forever new and unprofaned part of the universe. If it were worth the while to settle in those parts near to the Pleiades or the Hyades, to Aldebaran or Altair, then I was really there, or at an equal remoteness from the life which I had left behind. Thank you very much. Diane, I'm back to you.
Thank you very much. All right, we've got a couple minutes just in case anybody wants to do ask an astronomer a question. Any random questions out there that you're burning to ask our astronomers? Tom Hagan.
The 4 Galilean moons are all very distinct. They're all two. Is there any theory on that?
So our excellent question is, the 4 Galilean moons of Jupiter are very distinct. You've got icy Europa, you've got volcanically active Io, you've got very smooth Ganymede, very rough Callisto. Is there any particular reason why they should be so diverse? See, Jonathan's got his hand up.
I want to point out, I did not bribe this man, but this is a very good question to talk about in the presentation that you volunteered to give about the 4 Galilean.
Oh, yeah.
Okay, so Jonathan didn't answer the question, he did a pitch for a talk. Dale Parton.
Are you giving? Wow. I think that's most chipper about distinguishes
for, you know, and moons, not close but far there. Gravity of Jupiter is enormous. And, the moons are all slicing through it. Whether they get closer or farther. Not for that. When the closest one here passes by Europa, next paragraph, there's sort of a effect by the gravity of Europa. It's not huge, but it's there. And how these things flex Europa, you know, the Io. So the whole moon flexes slightly as it orbits Jupiter, and that warms it up frictional. So that's the closest Jupiter, so that's not hot. Yeah, it's huge, it's covered in clouds.
Yeah, I'm sorry, Dale. Can you come up here? I just realized.
Yeah, recap. It's got to do with how close or far it is from Jupiter, and Dale will take it from here.
How long do you want me to talk about this?
2 minutes,
2 minutes. Oh,
or 1 minute.
oh, you're killing me. Okay, so the 4 Galilean moons, the closest, the thing that most distinguishes, I'll make this as quick as I can. Thing that most distinguishes them is how close they come to Jupiter. And so the gravity of Jupiter flexes each moon slightly as it gets closer or farther from Jupiter in its orbit. That causes friction, it warms it up. So Io is the closest, so it's the hottest. And it has sulfur volcanoes all over the moon, like 400 some. And that's why it looks yellow orangish, all this sulfur stuff coming out of them and coming down on the surface. And it kind of goes from there. Europa clearly has an underwater, a subsurface ocean covered by very thick ice. Ganymede is the next farthest out. It's the biggest. It almost certainly also has a subsurface ocean. And Callisto, the farthest out, is the coldest, least affected by gravity. It may have an undersurface sea. And there's a lot of other things, like Ganymede is the only one of the 4 that's big enough to have its own magnetic field. The radiation levels at Io are totally lethal. You'd be dead within 2 or 3 hours in a spacesuit on Io. Anyhow, that's a little bit.
Sounds good. I look forward to the whole presentation. Jonathan?
Say, Ganymede's the only one big enough to have its own magnetic field from the core, but it's not the only one that has its own magnetic.
Okay, fair enough. All right, we do have a couple of minutes, and I mean a couple for observing reports. Has anybody been able to observe anything lately? Okay. It's been clear a few nights, it's just been frigid. So if a few people saw the moon, Jonathan.
So there's really beautiful conjunction between the moon and Jupiter. It's only about 2 fingers width so far. And then at the end of this month, it's going to be even closer. That's the same night. Tina corrected me. It's actually February 26th. So it's the week after the Belleville event. It's the week after the Cranbrook event. But that night happens to also be a conjunction. So if you want to come out to that, or even if you don't, just go outside and take a pair of binoculars and look at the moon and Jupiter.
Sounds good. And don't be fooled by the that Jeff going around of a smiley face conjunction with the moon, Saturn, and Neptune, because it won't look like that.
Not this
Yeah, I've seen it making the rounds. Okay, got a hand? Yes.
I think that could get one or two. Last night, not one guy that followed me was a truck driver and he was out in Colorado. And he had a C-Star S50 and he wanted to test out the remote feature that it has now. He let me log into his C-Star, be able to pull in the signal and then stream that. So that was kind of cool. It was just
Cool. Yeah, people are doing a lot with the sea stars. All right, any other observing reports? Has anybody seen any ice crystals? No, I mean in the sky. There's been several reports of daytime ice pillars hanging out. All right, Tom.
Massive.
Yes.
Midnight, last night, and the early mornings.
So good potential for aurora, you're saying?
Uh,
Possibly.
CME. Think they, biggest one in 9 years.
Oh my, biggest solar flare in 9 years. Very cool. That's why we need a solar group so we can stay on top of things. All right. Well, that takes us to the bottom of the hour, which means it is formally time for our short talk tonight. Over to you, Jonathan.
All right, so we are going to hear from Tom Hagen, our new radio astronomy special interest group leader. Tom has been an amateur astronomer on and off since high school in the 1970s. He, in addition to being a longtime member of the McMath-Holbert Astronomical Society, where he captained radio observing along with Marty Coons and Jim Shedlowski, he's also been a member of the Oakland Astronomy Club and the Society of Amateur Radio Astronomers. Tom's ham radio call sign is NE9Y. He's a retired electrical engineer who worked in the automotive industry, battling the electrical noise issues, not unlike what we're experiencing with the Cranbrook microphone wiring. He lives in Rochester, Michigan with his wife Kathy and cat Anna, and in his spare time, he rides his bike across Kansas. I'd like to hear more about that sometime. But
Well, this is from my LinkedIn profiles.
I have a keynote here somewhere. There it is. And it's not sharing on the Zoom. I am going to. Yeah. I'm just going to do entire screen. I'm going to set this to.
Then I can see my notes too, right?
We should be able to make that happen. Alrighty. So,
All right.
yeah, let me just try to change the Zoom share to, there we go. All right, does it look good on Zoom? All right, take it away.
Well, thanks, everybody. Again, I have volunteered to chair the radio astronomy special interest group. And yeah, let's get started here. I like both radio and astronomy. I'm an amateur radio operator. And I belong to, half a dozen amateur astronomy organizations, including Society for Amateur Radio Astronomy. All right, what do I do next here?
Just press the down arrow.
Down arrow?
Not working.
How about spacebar? No?
Spacebar works. Whatever you did just worked.
Is that?
What was that? Okay, here we go. Yeah, today's talk, I'm going to start with a little radio astronomy review. I like to do that for people who may not be as familiar with the subject. Then I'll talk a little bit about how these radio emissions actually are caused by Jupiter. And it's also the moon Io is involved with this process. So that's what kind of got me wondering about all the different moons of Jupiter. Then there's a project, a NASA-sponsored project called Radio Jove Project that people can participate in. They have a standardized setup. Okay. So now, can you see my cursor? How do I do that? Let's see it.
Let's see. Oh, actually, if you just, oops. If you just move it,
Oh,
it might be, if you wanna, I
you
can.
got to slide it over
if you,
there, huh? Oops.
yeah.
Oops, I moved it again. It's a little bit different.
Okay, there we go. Except it's not showing up. You may just have to point in the analog medium.
Yeah, okay. So anyway, this is the electromagnetic spectrum. And most of you probably know that light and radio waves are the same phenomenon. The only difference is, excuse me, the wavelength. So we have, this is a little difficult. We have the sun, for example, has a peak emission in the optical wavelength. Around the green line is where it actually peaks, and the wavelength is about 500 nanometers. That's 2,000 waves per millimeter, or about 25,000, 50,000 per inch. Then we're looking at tonight, going to be talking about Jupiter emissions, and they occur way down in the shortwave radio spectrum, wavelength of about 7 to 30 meters. And they, on this scale, they're almost to the end on the left there. All right. One of the neat things about radio astronomy is that they can detect things that are not visible in the optical range. Here is an image of the black hole at the center of the Milky Way galaxy. And this image was created by a worldwide network of radio telescopes called the Event Horizon Collaboration. The problem with trying to see things in the middle of the galaxy is there's a lot of dust and stuff down there. It scatters the light can't get through. Radio waves being longer can actually penetrate things like that. Then the main topic of discussion tonight will be the Jupiter-Io interaction. And here we have the beautiful Princess Io of the ancient Greek city of Argos being visited by Jupiter. He has a very jealous wife, Hera. He disguised himself as a cloud here. You can see his hands there. And then you can see his face real faint, kissing Io. But that's, of course, it's historical. It's not what we're really talking about tonight. Mythological. So he would disguise himself in various forms to hide from Hera, or Juno, his wife. And she would always find out, take his beatings. Didn't seem to matter. All right. So here is a movie that was made by a radio telescope array out at the Very Large Array in New Mexico. And it's a movie. There it goes. And we have, you can see the band of the Milky Way shows up really bright at these frequencies. This is a frequency of about 25.6 megahertz. And Jupiter, you see, it's flashing, it's going through one of its burst cycles down there. You can see it blinking on and off. This is actually speeded up quite a bit. This is 1 second of the video represents 1 minute of real time. So Jupiter is quite bright at this frequency wavelength. Here's how they did it. This is this array of individual dual dipole antennas about 500 feet across is in this field here. Each one of these antennas has 2 coaxial cables coming out of it, one for each pair of dipoles. It all goes into the white equipment shelter there by the porta pot. And that's where the picture is actually made. They take the information from individual pairs of telescopes. Every possible pair contributes to this picture, and it contributes frequency information. It's called spatial frequency. The computer in there takes all this information and does what's called a inverse Fourier transform to generate the image itself. You can see how big the antennas are to people. This is also the site of the first discovery of extraterrestrial radio detection. Famous astrophysicist Jody Summerlin. I don't know if anybody knows her name. Very little humor, sorry. Anyway, back to the Jupiter-Io interaction. Io is Jupiter's closest moon. Its period is about 1.77 days, roughly the size of the moon. And Jupiter itself rotates every 9.9 hours. Io is, hey, I lost a picture there. It's interesting. Io itself is subjected to these really intense tidal forces from Jupiter's gravity, as Dale mentioned. This is actually what brought up the subject of the Galilean moons. So these sulfur compounds get squeezed out of Io. And what's interesting is that I read that Io loses about 1 ton of mass every second due to this. Arithmetic's right, that's 86,400 tons per day. So why is Io still there after millions of years? Another question, I don't know. So as Io goes around Jupiter, all this material gets left in this plasma torus thing, it's called. And the material gets ionized by this intense radiation from Jupiter. And so we have a lot of charged particles out there. So as Io sweeps around through its own plasma torus, some of the material gets picked up the particles travel along the magnetic fields coming out of the north and south pole of Jupiter. The current is actually a few million amperes flowing in this tube. The electrical potential difference between Io and Jupiter is about 400,000 volts. So this is the thing that actually generates the radio waves as it moves around. Kind of a busy diagram here, but there are 2 longitudinal locations on Jupiter's magnetic axis. One is at 90 degrees, the other is at 240 degrees, where there is a disturbance that occurs by something called a cyclotron maser instability, or CMI. Don't ask me what that is, that's all I know. You'd have to dig into the academic papers to yeah, great, yeah, sure. So they're at 90 and 240 degrees longitude. So when this flux tube passes over these points, it generates a disturbance in the current. And anytime you accelerate or jiggle particles in this current flux tube, you generate electromagnetic radiation automatically. They also take the form of what's called synchrotron radiation. The electrons are spiraling along the magnetic fields going back and forth, and that is what causes the radiation. The strength of the magnetic field is what limits it to 40 megahertz at the high end, and at 10 megahertz, I guess, which is the low end. It's too dispersed to emit. So anyway, every time Jupiter rotates, roughly 10 hours, the longitudinal points pass through these magnetic loops or the flux tube, and you get a burst. So our Jupiter isn't radiating all the time. It only happens, under these special conditions. How are we doing on time? Good, okay. So like I say, it happens roughly every 10 hours as Jupiter spins. Of course, Io moves a little bit, every time Jupiter does one of his rotations. So it's probably closer to 10 hours. And most of the time, the radiation happens every cycle, but most of the time, of course, it's not aimed at Earth. It's aimed somewhere else. The shape of the radiation is a conical shape. And if the way this is drawn, we have Io at the 90-degree longitude. And if Earth was straight that way, in the exact line with Io and Jupiter, you would receive the radiation. It's like I say, it's formed in this conical shape like that. So it is directed. It doesn't go out in all directions equally. So to make it a little bit easier to predict, there's software that you can use. It's called Radio Jupiter Pro. And this is by a gentleman named Jim Sky, who's involved with the Radio Jove project. And the way it works, you don't have to remember all this stuff. All you gotta do is look at where Jupiter is on the position of this chart here. Here, I took this one this morning. There's right. The Jupiter icon is right on the lower right there. And it moves along these lines. These are hour lines for the day. The different colors on the lines indicate whether Jupiter is above or below the horizon. And then if Jupiter happens to pass over one of these hot spots here, you can expect some emissions. Of course, it has to be above the horizon. So this takes information about Jupiter's rotational center meridian longitude, CML, and the Io CML longitude. And basically what has to happen is, in order for us to hear it, Jupiter and Io and the Earth have to be in a straight line. And the one of these two hotspots, the EOB or the EOA hotspot, have to be right on the central meridian of Jupiter. That the central meridian is the vertical line that faces the Earth as we look at Jupiter. So those are the conditions that make it happen. Then there's a project that, again, NASA has sponsored. It's a standard setup where it uses a radio antenna that's a dual dipole array there. It's about the wavelength of the signal is around 15 meters. So these are half-wave dipoles, so they have to be half that length, about 7.5 meters. The output is a horizontal waterfall display. We have time along the bottom and frequency on the y-axis. And in that picture there, that guy's got a lot of noise. The vertical stripes are noise bursts, probably from local interference. These are what actual Jupiter bursts look like on this setup. You see this kind of swirly curved arc things. Those are actually bursts from Jupiter. Those probably EO A or B. Those are the strongest. And again, you can see the frequency on the y-axis, time on the x-axis, and it moves along with time. And then here's a different set. These have a different signature totally. They're more, excuse me, diagonal shaped. We have some, again, the vertical lines of some kind of probably local interference, and then down around 17 megahertz, you can see some kind of a continuous signal. It's probably, well, it is man-made, because man-made signals are very, they don't look fuzzy and curvy and stuff like the natural stuff does. And this thing does a very good job on detecting solar bursts. Here's I believe this was an X flare, yeah, from July or January 4th of this year. We had one, and you can, it's just a huge broadband burst of noise that covers the entire, bandwidth of the receiver. The diagonal line running through there is probably from a over-the-horizon radar system. You can see other man-made signals, the horizontal lines running along there at unique frequencies. So anyway, recap. Jupiter sends us intermittent radio bursts in the 10 to 40 megahertz range that we can detect when everything is lined up just right. So it doesn't happen that often. Equipment's pretty simple to use, and Radio Jove is a great place to get started on this. You can, there's user forums and tons of information and documentation, and being that it's NASA sponsored, they really do a good job setting it up. Thank you very much.
If we have time for one question, we'll break until 5 minutes after. Go ahead.
More of a statement than a question. The Europa, they think it has a planet-wide ocean underneath the ice. And that it's a possibility it could even have volcanic vents at the bottom of the ocean. Because the salt water in the ocean is contact with a rock core. And at the bottom of our oceans, we have volcanic vents that have life around the volcanic vents. That this life never sees any light. It's at the bottom of the ocean. So that life exists in a kind of chemosynthesis instead of photosynthesis. They live off the chemicals coming out of the vents and the heat. If it exists. So, sorry, nobody knows for sure, but there is a Europa Clipper mission that NASA launched and an ESA JUICE mission that will be looking at what's going on at that moon, for instance.
Did anybody have a question about the presentation? Parker?
So before you want to get involved or started in radio astronomy, how far could you get with a K on your dish?
I'm sorry, what kind of a dish? I don't know what that is. What is that? Oh, KU band?
K under.
KU, okay. You can, I've seen people have set these up to detect the hydrogen line emission from neutral hydrogen in the, from our galaxy. They've actually used the band as, they've actually used the KU frequency to detect the moon, which is kind of neat. I've never done that. The KU frequency is around 12 gigahertz. And that's the satellite frequency. Oh, there's tons of them for free now. And the people are getting rid of them. So. Yeah, they also make kind of neat thermal emission detectors. You can actually take one of these outside. You can point it at a tree, and you can actually detect the thermal emission coming from the tree at 12 gigahertz. Yeah, let's talk about it later. In fact, I've got one if you want to have it. Need to get rid of it.
All right, I think we better take our break. We're going to start in 5 minutes after, so we have about 10 minutes. But thank you again. And if you have any treasury related needs, you can see these gentlemen up here and they have grants. You can take your money or this. I don't know. Which is, now that I think about it, it's really a long sound. Five, 10, so. It was wild. It was very strange. Some of them were and then like better lights like shield. They did sort of there was like putting up just like no, it's like car hits. Yeah, and I rolled my window down to make sure it wasn't an airbag coming off the house. Somebody on that word.
I got cash.
Yeah, we're all just a bit straight.
Yeah,
That's where it goes.
yeah. It was just party where it's
Oh, please.
So wait.
Alright, so what are we for?
Just, my buddy's just preserving utility. Next Black Friday.
Alright, so
I have
the wasp.
Is there?
Well, it has to be the.
No, I'm gonna buy it. I bought the one, but it's not as good as, yeah, I bought the one that wasn't as good as that one, so I'll give one of the better.
Yeah, but please come out to Story and check it out.
Yes, I will check the last one.
No, I think Dale's in there.
He's excited. Yeah, he likes it.
So.
That's a different.
All this gets hung up.
You want to-
somewhere.
Well, that's an improvement picture.
Yeah.
That's.
That one I wanted to more for summertime. That one definitely be, because we went when it was freezing. There was, that was, oh,
This is a good state now. Yes, you were,
oh, mine's
right?
I wasn't giving you this is for the.
Okay, you already had more for this.
Yeah.
All right.
Open house is the way to go.
All I
This
do
is
is
trying to help make us this in order.
all right, cool. Thank you so much.
Okay, so that's that one. I can guarantee. I'll tell you if I'm gonna.
What?
Yeah.
Yeah.
End up in my back seat and then throw a brick on top of it and then be like, oh no, I ruined that calendar. Huh? No, but if that goes into my car, it's gonna get destroyed. It's like, you know, the open house is for a couple of weeks.
That's your seat.
That's for I have to say it.
We'll have to pay a house.
No, I mean, I'll keep it if you think.
Oh, t-shirts.
Crappy.
You're living in your car or something?
No, it's just my car's.
My friend is.
It's just for.
No, brother, he's in my school deal. I gave my friends. They're like, they call me for it.
Surprisingly tiny. And then. I know. That's great. No, I forgot. Fortunately, they need to click right down. Well.
So famously, they can't sell in virgin. It's legal doing it, so they don't get the.
Oh, interesting.
Yeah.
That's neat.
That was a deal.
Are you excited for DC four?
I'm very confident.
This year.
I think it's next year. It's all them within.
Okay.
Yours.
Yeah, I have CSR.
I really slap the
Yeah.
Can't take it.
Okay, oh, yeah, are you using, yes.
Okay.
What is your? Anything that has a PayPal, yeah, PayPal, actually PayPal is probably good. PayPal is actually probably better because on it, because, it's just more extra.
This is my third go. Last year.
It's on my side.
We're all sorry. And then I had this one. So, isn't, actually, can I see this, individual, did you want that? That's like, that's the national, Diane, can you unplug the?
Yes, or.
So you can, like, you get the.
Hi, sorry. Hi.
Should I plug in up here?
Yeah, let's just get this, all right, what sort of, you were using your computer?
Whichever. Yeah, I was gonna use this.
Okay.
Pick either HDMI or USB-C, whichever you prefer. So how does the sound work? Through this or through the
So through the computer on the stream and then through this for the room. So
Okay.
it's a little bit confusing,
I
but
see.
I think we should be good.
All right, let me see. Can I hide this stuff?
Sure.
Oops, I did the wrong thing.
Yeah, it should be.
Apparently,
Yeah, all you should need to do is
well, need to make this small again somehow. Sorry, it switched. I thought I was making it small, made it big, made the opposite. I'll show you why.
right.
I just wanted to make this window
Oh,
go
yeah,
away.
yeah.
Sorry,
Yes.
that's what I was trying to figure out.
Yeah.
That's what I did.
Ah.
I think it must be this, maybe the
It's
bottom.
this, yeah.
Yes, these all.
There.
All right, that's pretty good.
And then wherever wherever
Yeah.
that would be best to stay. All right. We're running a minute behind. All right, we're about to get started. If anybody wants to get in. Are you okay with having the lights up, or would you like to run the
Whatever you want.
I
Fine.
think as long as it's at least this visible, it should be good with the lights up.
Projectors are so bright these days.
No. I'm Indiana Jonesing my way out of this. Have fun. Jeff McCloud, the Clown McCloud. All right. All right, welcome to the feature presentation. Professor John Monnier obtained his physics BS from Purdue in 1993, followed by his PhD from the University of California at Berkeley under Charles H. Towns and William Danchi. Following a Harvard-Smithsonian Center for Astrophysics fellowship, Dr. Monnier began an assistant professor position at University of Michigan in 2002. Since then, his group has been responsible for development of the Michigan Infrared Combiner and the Michigan Young Stellar Imager at CHARA, which has the very fun abbreviation MYSTIC. The first instruments capable of infrared imaging of complex objects using long baseline interferometry. Professor Monnier is interested in all stages of stellar and planetary evolution, with a focus on imaging surfaces of stars and planet-forming disks, along with development of new methods for extrasolar planet detection and characterization. Please welcome Professor Monnier.
Not working again. This we're sharing.
Yeah, we're
a blank screen.
sharing a blank screen.
That's odd.
Yep, it's all white screen here.
All right. Is it
Say okay, maybe.
can you see anything on there?
All I got is a white screen.
Do you know Zoom had permission to share before?
Yeah, I Zoom all the time.
Okay, I'm gonna stop the share. You see anything on there? Yes, you do. Okay.
Yep, we do
All
now.
right. Sorry about that.
Everything good?
Yes.
Okay, thanks. Hi, nice to see everyone. So yeah, I wanted to try to just give a bit of a whirlwind tour of some of the science and technology that we are using and discovering with optical interferometry. So this is just, you'll see, all of these pictures somewhere in the slides today. All right. So the fundamental equation for imaging is the diffraction limit, right? So I know that with your small telescopes without adaptive optics, you're going to be limited by the seeing, right? By the atmosphere that where your sight is for any telescope bigger than this big, right? But you know that if you go to space and you don't have that bad atmosphere, or if you have fancy adaptive optics to fix the atmosphere, this starts to come in as limiting your resolution of the detail that you can see in an image. And it's just a ratio of the wavelength of light that you're observing at to the diameter of the telescope. That's a unitless number in radians. And so we can convert it to units that we like to use, right? Like arc seconds, to see what scale we can do if we had the biggest telescopes in the world. So in space, the biggest telescope is the James Webb. It operates in the infrared, and it's around 6.5 meter diameter. So if you plug in those numbers, convert it to arc seconds, you get a very respectable number here, 32 milliarc seconds. So that's 0.03 arc seconds. So that's better than you can do right in your backyard for sure. If you look at the Keck Observatory, that's the world's largest telescope on Earth. It also you can correct the atmosphere in the infrared to 1.6 microns, so not in the visible again. And it can get about 10 meters, and it has a fairly comparable resolution, again, around 30 milliarc seconds. And in the future, we're building the extremely large telescope, the ELT in Chile, and it's going to be 39 meters across at its maximum distance. And that way we can get down to getting to really low numbers here, around 9 milliarc seconds, or a hundredth of an arc second. So this is what the state of the art is now in the foreseeable future with single telescopes, so single aperture, large telescopes on the ground and in space. So let's just pop those resolutions up against what are the sizes of stars. I don't know if you ever calculated the size of stars, but you know roughly how big stars are in solar radii, and we know how far things are in parsecs, right? So you can just plug those in and get a decent idea of what the size, what kind of telescope you'd need to image a star itself, like to actually look at spots on it or something like that. So here's a graph showing it's a plot of the brightness of a star versus how big it is. So as you might guess, generally speaking, if it's brighter, it's bigger on the sky in angular units. And it also depends on the color, right? For the same brightness, something blue is smaller, something red is bigger, right? Like red giants. The biggest star in the northern hemisphere sky is Betelgeuse, 40 milliarc seconds. So if you look at the very, very top corner here, you see that it has up at top says what size telescope you would need to actually detect the size or measure the size of one of these stars in the universe. These are nearby stars. And you see that if you're up here in that upper right box, which includes the world's largest telescope today and the world's largest in 10 years, you see there's only about, you can count them up, right? There's like 10 objects maybe. That's in the future. If you look at 10 meters, there's basically only like 1 or 2, like Betelgeuse, So with current technology, with current single telescope technology, only a few stars are anything but point sources. And even with the world's largest, you see all we're going to do is have around 10 objects. All of them are red giants. So what would you need? Well, you can keep going to the left to see at what point do you start to be able to resolve a lot of different kinds of stars, not just in number, but also different colors, from hot stars to cool stars, and eventually even to, say, planet-forming disks, which are down there and below that, these sort of sequences here, because they're even colder than red stars. And you can see that if we look at I'll introduce these acronyms later, but the VLTI is an interferometer in Chile that can get up to around 100 or 150 meter resolution. And you see with that interferometer, you see that it can do now, look, hundreds or thousands of stars, although you notice they're pretty much all red stars. They're all still red giants. Although there's some, you see there's a few green ones, some yellow ones. So there's starting to be some solar type stars or intermediate temperature stars that you can observe. For instance, Alpha Centauri. Alpha Centauri, very solar type and very nearby. So VLTI can do Alpha Centauri, for instance. But CHARA, which is the interferometer I'll talk to you about, which is the one outside Los Angeles, it has the longest best resolution or longest baselines. The telescopes are the farthest apart, which gives us the power of a much larger telescope. And what's great about CHARA is you can see we're really getting into a sweet spot where we can start to see all kinds of different stars with CHARA. So it's sort of been explaining why CHARA has really opened up the window to the universe compared to, say, previous systems, because if you just look at the universe, there's a certain critical resolution you need because, stars are far away. Even the closest stars are far away, right? So it just, it's one of these cases where you might improve your technology by a factor of 10 and you're still too short. You do another factor of 10, you're still too short. But then you get a factor of 10 and then all of a sudden lots of things become possible. So sometimes in science, right, we have these thresholds where you just need to get to a point and then the world opens up. So like gravity waves, right, with LIGO. We had 50 years of not detecting gravity waves and now they're detecting them all the time, right? Because they just get to that point. So that's where we are at the moment with interferometers. So let me say more about what an interferometer is. But let me also touch base with a group like you guys, because one of the cool things about interferometers is we are looking at the same stars that you're looking at a lot of times. We are looking at, if you look at H magnitude there, you see the number is around 5, right? So that's not V magnitude, but it's a basic idea that these are naked eye stars that we are imaging. So the stars I'm going to show you today are almost all stars you can see with yourself, with your telescope, even with the naked eye, let alone with the telescope. So it's kind of fun, I think, to be able to kind of open up, points of light that humans have been, any human, from thousands of years ago could see some of these stars, right? If I met a Greek, if I met Hipparchus, right, we'd have a great conversation about the rapid rotators that were imaging that he was first to document. Okay, so basic theory of interferometer. So let me just give the concept. So the only physics you really need to remember or know about interferometry is that light is a wave, and that if you combine light from very far distances, that they interfere, and that they interfere to create what's called a fringe or this sine wave. So if you imagine having two different stars that were close together in the sky, they'd be coming in at slightly different angles, almost the same angle, right? But slightly different. So when they go through this little two-slit experiment, they each project a pattern, but because they're coming in at different angles, that pattern is shifted one with respect to the other. That means the peaks don't line up, right? The peaks of one are slightly off from the peaks of the other star. So when they add up in your detector, they would give you something that isn't what either of the originals, but depends on if they're constructively or destructively interfering. And so we can see here the two different, you can see some different plots here, the green and the red, but what's left at the end is the black, which you see is slightly shifted to the right, and you see that it doesn't all the way go down to 0. It's not 100%, it doesn't go destructive completely because the troughs and the peaks partially overlap each other from the two stars. So if we measure this, we could tell you that the object we're looking at isn't just a single star. It must have more structure, more complexity to it. Now, mathematically, to interpret it, we need Fourier transform. So luckily, it turns out this measurement of an interferometer between two telescopes is what's called one Fourier component of the image that you're looking at. So Fourier theory is this idea that any image can be made as a combination of sines and cosines. So lots of these waves that you see here. So if you knew all the sines and cosines, you could add all those cosines back together and make the image again. But we're stuck with only some of the sines and cosines. So if we had all of them, we could just add them up, make an image. That's what a telescope does. A telescope gives you, essentially, think of a telescope as an interferometer, except every possible separations of your interferometer are inside your aperture, except when you get to the maximum. So that's great because you basically measure all the sines and cosines and you can make an image. Interferometers are harder because we don't measure them all. So we have to we have to do image reconstruction. That is, we have to kind of invert a mathematical problem. So there's some issues with that. Now in practice, we don't really have a two slits. What we have is two telescopes. We have long vacuum pipes connecting them to a central combiner where we have to add what's called the delay line to compensate for the geometrical delay. So when an object comes from the side, from southeast, it hits the wave fronts, the light from the object hits one telescope before the other one. that's some sort of, less than a microsecond of delay. Now, in order for us to interfere that light, we have to then put the one that gets there first in sort of a delay line to have it wait around till the other one gets there. And that's called a delay line. And I'll show a picture of that. So that makes it very complicated. So this is just the state of play in the world right now. The world's largest one is the one I work on, CHARA. So it's this blue center array that you show here. It has maximum separation of over 300 meters, and we have 6 telescopes. Now, the telescopes are relatively small. They're only 1 meter, which is something we'd love to fix and make bigger. But right now, we're limited to 1 meter. The very large telescope array has shorter baselines, but they have the ability to use their 4 8-meter telescopes, which is incredibly powerful to have that big, to have your interferometer with 8-meter telescopes. So they can look at very faint things, but they can't see as like to the small details as we can do. There's a visible light interferometer that the Navy actually operates called the IMPOI. You may know the Navy has been historically keeping track of astrometry and where the stars are originally for navigation at the sea, on the seas, right? That's how they could do their navigation. And so they've historically kept some of that role. Currently, they're more interested in using their interferometer to image satellites and to see where the satellites are than they are to do the stars, but they're still doing some astronomy. And lastly, there's a really powerful telescope in Arizona, the Large Binocular Telescope, which are 2 8-meter telescopes, so they're very big, but they're separated by and only 23 meters, so relatively short. That's this one at the bottom here. So that's kind of the full play right now of optical interferometers in the world. Okay, so CHARA. CHARA, just to give credit, CHARA itself wasn't built by Michigan. CHARA was built by Georgia State University with funding from the National Science Foundation and the Keck Foundation. And it's built and it was, still is operated by Georgia State. They get money from the state as well as from from grants to keep it going. But it has a lot of collaborators. So it has collaborators in France, in Michigan, Australia, and in the UK that has contributed different things to the array. As you'll see, what I've contributed in Michigan is some of the instruments. So they built the big infrastructure, the telescopes, the delay lines, all that stuff. And all that light comes together, and then you have to, of course, do something with it and detect it. And so that's the part that I've specialized in. So here's a picture of Mount Wilson outside LA. Have any of you been to Mount Wilson here? So that's the Hooker telescope. That's a 100-inch telescope that Hubble used. So this is the famous site that used to be the world's largest telescope from in the 20s and 30s and early 40s. This was the world's largest telescope. That was before LA was a big city and the city lights weren't such a problem, right? So obviously, eventually they moved the big telescopes to other mountaintops. But for interferometers, as you saw, we're looking at naked eye stars. We're looking at 10th magnitude stars. So at that point, the city lights in the background is still negligible for us. So it doesn't bother us at all. And it just turns out that this site has an amazingly good seeing for at least some of the year. So because it's right on the ocean and the flow from the wind flowing over the ocean is very laminar and smooth. And so as long as you have a wind coming from the west, you can get quite good seeing because this mountain is the first one of the range. Okay, I don't know if you can see our array, but we're these little domes here embedded in the forest. And if you look, you see these lines connecting them. Those are these vacuum pipes, kind of like photon aqueducts, that go across the forest, putting our photons together without getting even more turbulence from the ground layer. If we had to shoot that across the, across the windy air, it would be terrible. So that's our maximum baseline there. So imagine when you see this, you're supposed to imagine a telescope, the power of a telescope that is that entire size, right? That's what we're going for here. Rather than having to have a telescope that big, which is far beyond what we can do, we are doing pieces of a telescope that big and combining it together. That's the concept. So if we go in, so in this big building, oh yeah, let me show you. So this big building, do you have a laser pointer by chance here? Is there a laser pointer here? No. So anyway, this big building right by the 100-inch, right? You see the big dome, and right south of it or lower below it is this L-shaped building. And that's the building we're gonna go inside right now in the next video. And that long building that way is used for this delay line purpose, because you can imagine something coming, hitting this telescope first. Look how long until it, gets all the way to the other telescope. The light takes a long time to go 300 meters. So we have to bounce that back and forth like, 4 or 5 times in order to try to account for that. So what you'll see here is a look down that long building. And what you see underneath, see that tube underneath? That is a vacuum delay. So that's in vacuum still, and it can go all the way. In fact, it goes through that wall into the next room and then bounces back. So it's just like a mirror like this. So it goes all the way, or no, it's actually just a flat mirror, actually. Just a flat mirror. So it just goes all the way halfway to the flat mirror and then all the way back. Now that's one length. Then it comes back up, and then these rails that you see actually are kind of like a railroad, where we have moving mirrors that we have to adjust as stars move, because stars don't just sit in one place, they rise and set. So that delay we have to correct is changing constantly, and we have to keep that delay perfect at the level of a small fraction of a wavelength of light. So that's called the delay line trolley, and just for simplicity, it's in air. It'd be nice if it were in a vacuum. Some interferometers have it in a vacuum, but that's a lot harder to do, as you might guess, since there are so many moving parts, and if it breaks and trying to deal with it. So we have other methods of doing it like that, by keeping it in air. So we go through this long, like I said, back and forth 4 times. Then we turn the corner. We have to keep the beam big for diffraction purposes. And here in this table, we shrink it back down again. We choose which beam we want. We turn a corner, and then we go into this room, which has all the different instruments. So essentially, like in a big telescope, you have like a mirror that can say, okay, send the light to this instrument, or you turn the mirror, you send the light to this instrument, or maybe you move it out of the way and it goes to Cassegrain through the hole in the primary, right? You can choose different instruments. Here we have a similar idea where we have a switch yard where we can send the beams from the 6 telescopes to different instruments, with just clicking a button. So we have like 5 different instruments that have different specialties depending on the science you're doing. What wavelength, with visible light, infrared, 2 different kinds of infrared, stuff like that. So there's a lot of optics in a very crowded room. So this just shows one of the instruments that I built, where what we do is we take the 6 beams here coming in from the left, and I'm just going to walk you through how we do it. It's just kind of cool use of technology. We come in and we go into a mirror, which is an off-axis parabola, and we focus it down into each telescope gets into one single mode of a fiber. And we take that single mode fiber, and then we can route it and do stuff with it, and we've had it now controlled. So in this case, what we do is we put it in a fiber, we then put the fibers in a pattern, and then we sort of recreate that 2-slit experiment, I showed at the beginning. So each of the beams now will combine, and each of the pairs will make a interference pattern that we can measure. So like a single beam will make a fringe like this. Because we want to measure the wavelength too, we actually we compress it in 1 dimension into a slit. And just like a spectrograph, we can put this slit into a prism and disperse it, and we get wavelengths and interference all at once. And since we have 6 of these, we actually get every pair. I'm only showing 1 pair of fringes, 1 fringe from 1 pair, but when you have 6 telescopes, you can make 15 pairs. So in fact, in real life, this has a complicated pattern of 15 fringes all overlapping each other. Okay, that's just a little bit behind the scenes of the combiner of how we do it. So let's look at some science. So one of the first things we did was wanted to image the surfaces of stars. And one of the stars that had never been able to be done before with the earlier interferometers was rapidly rotating stars. So, unlike the sun, which rotates every month or so, some stars, can rotate like every 8 hours or 6 hours or 10 hours, right? So these are the famous rapidly rotating stars. And this, in theory, should cause a star to become elongated like a pancake along the equator. And another thing that was predicted is that because the equator is farther away from the core, you know, all the energy is coming from the core and it's coming out, the prediction is that the equator should be darker. It should be cooler. You're basically farther away from the energy source. These effects were never before observed because there's no way to observe them, but they were certainly predicted and a lot of indirect evidence for it, but no one actually could see it before. And that, anyway, rapid rotation itself causes a number of things like mixing, and it affects stellar evolution. It, you know, affects how things explode, like in the massive stars, like what kind of, you know, gamma ray burst versus a type of supernova. So that it's needed to understand how rotation affects stellar structure. So here's an example of a star. If you have no spinning, it just looks like this. It's darker on the edge just from, you know, limb darkening, which you've probably heard of. The sun has limb darkening. The edges appear cooler. So if we spin it up, at first, you know, we're spinning it up, not much happens. But when you get above 60, 70, 80% of the maximum spin, you really should start to see it spreading out and cooling down along the equator. So we were able to look at 6 or so of the brightest rapid rotators. So these are all stars you've heard of. So here's just our gallery of images. So the first one we did was Altair. So Altair, you know, summer triangle object. This is what Altair actually looks like, and we were able to see that it's cooler along an equator, and we saw that the polar regions are hotter, and this helped us prove these theories of gravity darkening and oblateness. But we were able to do a lot more. We have Alderaan, that's Alpha Ceph. We have Rosso-Hague, Alpha Oph. You know, these are all alpha, alpha, alpha. We got Regulus, Alpha Leo, and maybe one not as famous, Beta Cas. Beta Cas. In fact, we're a visitor. We're working on this source right now at Michigan with a visitor where we have some new data on Beta Cas. So this just is, again, and the science of this is that we actually fit models to these images and that we can try to see if the amount of darkening, for instance, matches theory. And it didn't, in fact. The theory predicted one thing, we measured a different thing, and then 5 years later, there's a new theory that seems to explain it. So we're still trying to, you know, keep going on the cycle of science and work on that. Another cool thing we looked at, which again are very common to look at with, you know, in amateur astronomers, are variable stars, right? Especially interacting and eclipsing binary stars. So Algol is one of the most famous, one of the earliest identified, right, eclipsing binary star. Here's its light curve. You know, it's a bit faint, but it's a visual magnet of a naked eye star. And so we are able to take images of this system both out of eclipse here, where we actually see for the first time a star that is elongated not from spinning, but from what's called Roche lobe filling. So you may know that if two stars are close together and one star is really large, it will start to feel the gravitational effect of the other and start to look like an egg shape. And so that's what this shape is coming from, it's almost filling its Roche lobe, where it will now, if it completely filled it, that material will start to fall on the other object, right, and fill it up. And then this is a cool image we made that happened to be right at eclipse. And I think you can see it does look like one star is now in front of the other star. So that's awesome. Another famous system was Beta Lyrae. I think this movie is on Wikipedia page. This is, again, another famous eclipsing binary, 13-day period. This is an interesting system because its Roche lobe filling object is overflowing, and the primary is completely surrounded by gas and dust, or gas, I guess, not dust in this case. But look at that separation. This is only 1 milli-arcsecond. I mean, this is incredibly tiny. But we observed it in a series and actually made a little movie of it here. So this is actually showing this movie of the interacting binary. So yeah, that's just crazy to see this come to life. Now, how many of you heard of Epsilon Auriga? I don't know how famous it is. It's famous, but it hasn't done much since 2010. So it'll get more famous, and it's 27 years after that. And in 2037, you'll hear about it again. So it's a source that was identified over 100 years ago as having a very long eclipse. It had an eclipse that lasts over an eclipse where it loses half its light for like 2 or 3 years, or 2 years, which is, you know, ridiculously long. And it was eventually figured out that it repeats every 27 years. So there's some kind of system that is a 27-year period. So it's like an edge-on binary, presumably. But it can't just be 2 stars, because the 2 stars crossing each other wouldn't allow, that eclipse would only last, you know, I don't know, weeks or days, not a year or so. And the only thing it could be is something that some other disk. So again, so now we have to postulate there's 2 stars that are on an edge-on system, and there's a big cloud or disk around the, you know, one of them that causes this very long eclipse. And after many, you know, 100 years of data collecting, in the 80s, they put it all together and they came up with this idea of what we would see, what they thought the system was. There's a giant star in the background. There's an unseen star. We've never actually detected the other star in its own light. And that's because presumably it's blocked by its disk, which is itself edge-on. And this whole double edge-on system is, you know, has this sort of a geometry where it crosses over it. And there's a lot, you know, we can get into why they think it's this way. There's lots of clues, right, in the astronomy, like what is, you know, how does the eclipse look at different wavelengths? How, you know, what's the polarization behavior? What are the lines doing during the eclipses? So there's lots to it. So there's a lot. I'm not, this was actually a very thoughtful image based on a lot of data that seems to explain everything. So we went to look at it. So this was our image of Epsilon Auriga in 2008 before anything happened. And there's probably some spots going on, we think, on this giant star. So the first image we looked at, it remarkably looked a lot like the prediction. You know, this is one of the few times that, in my experience, that predictions come true in astronomy. And you can see it looks like somebody, you know, just the finger of God here, just sticking its finger in front of Epsilon Auriga. And sure enough, we kept observing it, and it got bigger and bigger. And crazily enough, I mean, it's a semicircle star here during this eclipse. It just looks like a semicircle. And that explains what you measure. We said it lost half its flux, and it's completely in agreement with this great model by Kemp. So we took even more data, and the student, Brian Kloppenberg, who did his thesis work on this, did a really cool thing where rather than make a movie, like I just showed you, kind of watching it go across, you can do something else, which is you instead of moving the disk, the disk across the star, let's stop the disk, you know, simulate this disk being stopped and move the star behind the disk. This allows you to make what's called a silhouette image, right? So this disk is here, and we're going to move the light beam behind it and put all our images together. And this is the amazing silhouette of this disk that we measured. So that disk that was hypothesized, I mean, you know, we can't see it directly because it's edge on and cold, but look at that. You can just see it, right? That line at the bottom, that this is an extremely thin, dense disk. How this got there, nobody knows. Like, there is still no good explanation that can explain. I mean, you can make up an explanation, but the fact that it's around like a 3rd magnitude star is crazy. Like, this is probably a very rare situation, and that it happens to be so close to us is just wild.
The brighter spot towards the center of the disk?
We didn't. I mean, you can see this is when it went behind the sun, you know, the sun. So since it's such a long eclipse, we only can observe it for a part of the time. So you can see we got kind of close to the middle there. You know, that brightening in the center, I don't know if it's really true, like if it has happened every time from what I remember, so that's not clear. It doesn't seem to necessarily repeat exactly the same each time, or the data has been different. So lastly, just to get to a few more cool topics. So I showed you rapidly rotating stars. Another kind of star to look at would be stars that have spots on them. Now, earlier, before CHARA, people had discovered spots on stars, but they were giant stars, like Betelgeuse, right? Red giants, red supergiants. They are super huge, very low gravity, and they have a huge amount of convection, which causes a huge generation of spots, you know, as big upwellings of hot stuff come up, you see the top of it being hot, then they cool down and they sink, and just huge convective cells on red giants that are, you know, many AU across, or and for the case of Betelgeuse, for instance. So that's one type of spot. Now, but, you know, on the sun, we have different kind of spots, right? We have magnetic spots that have to do with magnetic fields that clamp down on, it's the opposite. They clamp down on convection, so the hot stuff rises around them. And so you see cool spots where you have very strong magnetic fields. You know, the spots in the sun are very weak, you can see them, of course. They can be somewhat strong, but it's hard for us to use. We're trying to get to the point of doing that with our technology. But there's a special class of star called RS tan bands, which have very strong magnetic spots. And this was one of the best ones called Zeta Andromeda. And this was Rachel's thesis topic, where what we did is it rotates every 18 days. So what we did is we took an image like every day that we could without, weather permitting. And then we took a model where we took the surface of a star and we know it's how fast it's rotating. So when we see it with the interferometer, we're seeing the different sides of it, right, as it rotates. And so we can analyze that data together to make an image on a surface of the sphere. So we can basically see all the way around it at the same time because we've used all the data together. And so this was our movie that we made of that. So it should start here, I thought. Oh, geez. Oh, man. Oh, no, sorry, it's not working. Well, it was on the front page. It was working on the front page. Not sure why it's not working now. Sorry about that. Weird. But anyway, oh, there it goes. So this is our movie where you can see these very strong spots moving around. And what we found, for instance, was that the spots are pretty chaotic and not very symmetrical. So, the sun, you have bands of spots that are mid-latitude, north and south. This is highly asymmetric. There's no obvious symmetry between the north and south at all. In fact, this one has a very strong dark spot on the pole, which is not seen on the sun at all. So this is a different mode of magnetic spots. It's much more extreme than the sun, and it's showing us some new physics about magnetic fields in stellar dynamo theory. Now, the reason that these stars are so extreme is because they're actually spun up by a binary. So in this left one, we haven't been able to detect the binary. We think it might be a white dwarf because on the right, though, it's another star. And we've measured its orbit, which you can see some of our data there, and you can see how the spinning of the giant star there is synchronized with it. And you can see the spots on this object are different, sigma gem. All right, now what else can we do other than stars? Well, every once in a while, you probably know there's novae that are so bright that you can also see them with the naked eye, right? So this was one such object, Nova Del, back in 2013. Where you can see it went up to about a bit above 5th magnitude, so just barely visible. And then it fades. And there's different kinds of novae, but this one we observed with CHARA, and what we saw was, at first it was small, and 3 days after it was small, but not a point source, and you see it just grew, as you might guess. It just grows as this blast wave from the nova gets bigger and bigger. And this is the first one of a few that we've done now. We had a recent press release last month where we did a few more of these. And each one we've observed are somewhat different. What's interesting about this one is you can see kind of the asymmetry start to change as it starts to evolve. And that's kind of cool because most of the time in a nova, you're only seeing the aftermath where the explosion blasts into all the circumstellar material around it. And so what you're seeing like a month later or a year later with the VLA or something is more the effect of the environment, because the initial explosion has been lost in the mass of the shell, which has been swept up. So you lose the details of the explosion at that point. Here we're trying to see like how does the actual explosion go? Is it bipolar? Is it elliptical? Is it one-sided? This is what we hope. By looking at it within days of when it blows, we're only seeing the ejecta. We're not seeing just the environment. And we're hoping that with more data, we can learn about how these explosions happen. A new thing we're doing is called astrometry. So astrometry, is when you measure the position of a star very precisely. We can measure stars relative, well, when we measure astrometry, because of the turbulence of the atmosphere, we can't measure them in isolation, but if you have two stars close by, we can measure their relative separation. So, and let's say a binary star. So if you have a binary star and you think maybe it has a planet around it, one of the stars has a planet, right? You know that would cause a wobble. It would cause one of the stars to move in a pattern, right? A wobble as the unseen planet is moving, shoving it around. So we have a project to observe a bunch of binary stars to look for planets. This was our first data set where we looked at a binary star, and we looked at it in sort of every 5-10 minutes, and we could see this motion of the star. This is no planet, but we could see it moving in just 10 minutes. And look at the scale. This error bar here is like 10 micro arc seconds. So we're talking about milli-arc seconds. We're now 100 times smaller than that. 10 micro arc seconds. So 10 micro arc seconds is like 2 centimeters on the moon. So this is like looking at a few feet of motion on the moon, if you want to imagine the angle, how tiny of an angle this is. So this is to show how much big of a boost this is. This was an example of a wobble for one system called Kappa Peg. This is a triple system, so no planet, but you have 2 stars in a 100, very long period orbit, and then one of them has another star that's causing a wobble. And you see the wobble's small. You see it's less than a milli-arc second, right? It's pretty small. And this was the previous state of the art. With our system, with CHARA being 10 times bigger, better, here's our orbit. Look at our data points, not those big circles over there. Now we're seeing it at this level now. So it's really a breakthrough that we are still sorting out, that we're still taking. It takes a lot of data to do this work. So we're still collecting data now to look for planets. Okay, I told you it's a whirlwind. Another cool thing we're looking at is planet formation. So young stars, where planets are actively forming are not that close to us. It's relatively rare, very short period. It only lasts for 10 million years. So the nearest one is like 100 parsecs away. Then you get to Orion, a massive star forming region, Orion, 300 or 400 parsecs away. So that means that it's hard to image them with single telescopes. You can't see in the inner, like the solar system scale is hard to see. So for instance, here's an image of a disk around a young star in the millimeter wave on ALMA, and we see it's kind of like a debris disk. It's actually interesting. There's a ring at many hundreds of AU. See, if you look at the bottom field of view, that's 340 AU. So that's, a few times our solar system scale, right? And if you look in the center in the infrared, we can actually see, and this is a very dynamic planet forming disk. We see this very set of spirals and scattered light. So this is showing light from the star that scatters off the complex dust around it. And even though that looks amazing, the resolution is amazing, but you can see the scale is still solar system scale. If you want to look at where Jupiter is or where the Earth would be in 1 AU, it's in the center pixel. Like you cannot see it at all. So with interferometers, we're trying to dig into the center pixel there. So now we're down to, you see 1 AU, 2 AU by 2 AU. So now we're really in that inner solar system. And that's where we want to be if you want to look for planets forming, because not many planets are forming at 100 AU, for instance. Now, what do we see here? You notice what we see is a ring, and we see a black, dark, it's dark in the middle, and there's a star in the center. So why is it black in the center? Well, this was predicted because when the dust from the disk gets closer and closer and closer, it gets hotter and hotter and hotter, and at some point, dust can't exist at such high temperature, so it evaporates. So it has been predicted that there should be a hole in the center, right? Because the dust is now turned into gas, and gas is a lot more transparent. Light can go through gas much easier than it can dust. And so that's exactly what we're seeing here. Here's probably our best images that we have of a source called V1295 Aquila, the more massive system. You can see we labeled the orbits here of, let's see, 0.4 AU. It happens that this ring is about exactly 1 AU, it just turns out. And we saw in 2 different data sets taken a month apart, we saw some changes. For instance, this bright spot on the bottom right here seems to have moved. We're not 100% sure because we don't have that much data yet. This is a new result from last year, but it could be that we're seeing some structure, some motion. And one of the reasons that we think could cause this is if there's planets forming here. So if there was a planet out like a little farther out, it could kind of shepherd spots. It's kind of like in Saturn, where it would be in synchrony with some features closer in, farther out. So this is an active area now that we're trying to really focus on a few objects. Spend a lot of telescope time observing it all the time to see if we can see spots moving. So stay tuned on that. So yeah, this is just, again, give you the artist visualization and what the real life images kind of look like, where we're seeing this, again, this region here, this dark region, right at that inner wall where the dust is so hot, it's 1500, 2000 Kelvin, where it's just being turned into gas. And I'm just going to close with technology and our future, where we're going. So a lot of the advances recently is with improved technology. So I'm going to just mention the new camera technology called the EAPD camera. We've been taking advantage of cryo coolers, so we don't have to use like liquid helium, liquid nitrogen anymore. We can use these very affordable and robust cryo coolers. We use single mode fibers, and I'll show you a picture of what's called integrated optics technology. It's an analogy to integrated circuits, where we can put beam paths on a piece of glass rather than with mirrors going across the room. So first, just to show you this amazing result. So here's an image of what we had to live with, before 2015. There's a fringe, there's an interference pattern there. You can probably see there's some up and down going there, right? But it doesn't look that great. But this is what we had to live with. Now, this new detector was made such that every single pixel on the camera had what's called an avalanche photodiode. This is basically, it's like a photomultiplier tube, right? Where you have one electron, kind of gets accelerated by a field, it hits other electrons, makes 3 more, each of those then avalanche more, and so one event becomes 100 or something, right? So you can see individual events. But they figured a way to do that within every single pixel. So rather than being a big chunk of photomultiplier tube, which is literally like this big, they make them 24 microns across. And so with that technology, we go from this to this. So it just blows your mind, right? Like, that was a huge advance that allowed us to go from imaging only Altair, which was great, but Altair is first magnitude, right? It's kind of bright, to the young stars, which are 7th magnitude, right? A factor of 100 fainter, more than 100 fainter. So the other cool thing is integrated optics. So this is where, rather than have all these beams bouncing around, you can put the beams into a chip on glass, and by changing the index of refraction using different technologies like ion etching or laser writing, you can guide the light along these paths and then cross them, interfere them, do all cool stuff. So this is how it actually looks. So we have the fibers mating to these little wave guides, and then they do what you want. And so this is an example of 4. You can make them with 6 or 8, and you can do lots of cool tricks with this technology. So this is how it really looks at CHARA. All right, we're just winding down to the real futuristic. So we were excited to try to figure out, well, what could we do if we wanted to, I showed you those images of young stars, planet-forming disks. We've discovered lots of exoplanets, right? Over 6,000 now. But we don't really understand all the patterns, right? We see a lot of, super Earths and sub-Neptunes, and we see different, dependencies on the types of stars that are formed around, all this stuff. It doesn't fit our solar system. We need more data. And of course, one of the cool ways to do it is go look at planets forming now and try to see what they're doing as they form, right? And so we wanted to design a system that could image all the stages of planet formation, as they were happening. So we just took a simulation. So this is a simulation, but it's a very good 3-dimensional simulation of planets forming. And you can kind of see the planets forming there, those little bright dots in various spots. And you see the feeding and the streams and the cavities, all kind of the complexity, right? Planet formation is going to be very complicated at its early stages. And so we tried to figure out what could we do with that. So we took this image here, and first we tried to look at what if we could detect the planets in the system. And so we found that if we had 21 telescopes, that's a lot, 4 meters though, not the biggest in the world, 21 4-meter telescopes, we could make an image on the right here where we can detect all those giant planets forming. So if we could afford such a thing, we could really unmask at least the giant planets as they're forming, which would be nice. Although it's very hard to do below giant planets, unfortunately. We also tried to say, could we see a planet solar system like our own? Like, could we see Jupiter? Could we see, Jupiter forming? This tries to be a match to our solar system. And if we had here 8 meters, we had to have 12 8-meter telescopes. We had to go to even more expensive telescopes to do this. But you can start to see, we could see Jupiter, and we could see the gap Jupiter is forming with such a powerful array. Unfortunately, this costs way too much money right now. 8-meter telescopes still cost like $50 million each, Surely you could make them cheaper if you were making, 10 of them, but nonetheless, we estimate this would be getting to $1 billion project, which seems too expensive. So we need to invest in better technology, cheaper telescopes. Like, can we make telescopes cheaper? The other option is to say, all right, forget about the ground and go to space. So as you know, space could be is great in many respects, right? It doesn't have the thermal background from the warm atmosphere. It doesn't have turbulence. You don't need delay lines because you can just fly your telescopes wherever you want them in space in theory. So space would really be the best place for an interferometer, but we've never flown an interferometer. And in fact, formation flying of spacecraft is very new thing. So we proposed at Michigan a new mission called STARry, which is trying to demonstrate one piece of the puzzle. So it's not doing interferometry, but it's trying to show, can we bounce light across hundreds of meters from one telescope to the other in a controlled way? So that is a step that if we think that if we can prove this, then doing an interferometer where we have to add more telescopes is something that would be considered lower risk. Because right now, even this hasn't been done, right? And so we need, in space, you kind of have to do things in steps. And so an interferometer, let me just skip ahead. The ultimate dream of interferometer in space is this mission called the LIFE mission. In the LIFE mission, we are going to do interferometry in the mid-infrared, and that is the wavelength that the Earth is brightest at, right? The Earth is peak of its black body curve is in 10 microns at 300 Kelvin. And this is, if we want to look for biosignatures, signs of, water and oxygen, ozone, molecules like that, this would be the best place to do it. NASA, you may have heard, is working on a mission called the Habitable Worlds Observatory. It's meant to do it in the visible light, which is easier in the sense that you can do it on a smaller telescope, but it's harder because this Earth is not very bright in the visible. It's just reflected from the sun. It's 10 billion times fainter. All right. The Earth is 10 billion times fainter than the sun, so it's a very hard problem to do. While in the infrared, it's only 1 million times fainter, so a lot easier. All right, so anyway, just to cut to the chase, we're working on this CubeSat, this small sat project called the CubeSat. We're doing some work now at Michigan. I just want to show that this is a new thing for us. So it's a 5-year plan. So we're hoping to launch in 2029. We're sort of 1 year in. Eventually, the next step will be to do it with 3 telescopes like this and do interferometry, say, in the next decade. So I will just end there and say thanks, everybody. Here's a lot of our pictures. Thanks.
Well done. Thank you.
You talked about imaging stars, exoplanets. The Cassini mission to Saturn clearly took pictures of water geysers coming out of Enceladus. I think it's the Hubble that took some pictures of Europa that may have seen geysers, but it wasn't here. Can you image geysers on Galilean moons with this technique?
There's just not enough light, The resolution's there, but the surface brightness is not there. They're so far from the sun that the amount of light coming from that small region is too low for their current technology. We are able to do it on some, there's some work to do it with asteroids and Kuiper Belt objects, that kind of stuff. But I think, yeah, the large binocular telescope interferometer I mentioned, which is 8 meters, have done some of the moons of Jupiter, and so it can do, nothing can compete with just flying there though. So like, and in our own solar system, you should just go there. It's like thousands of times better than from here, even with, yeah. Yeah.
Go ahead. I think I read that of the, like, 6,000 extra solar planetary systems, they never found one like ours. They find a lot of large Jupiters that are very close to the sun. Well, that's my question.
Yeah.
I think that's possible that you guys would be able to do that one day, because so far from what I've read, there's nothing like our system where you have the terrestrial.
Yeah, it's very hard. So unless the Earth will transit in front of the, transit method, right? If it goes in front, if it goes in front of, if it goes in front of its star, then you can detect the Earth-like planet. That's the only technology that can detect an Earth-sized planet right now. And it just happens to be very rare. So Kepler probably would have seen some if it lasted another, if it made its full, Kepler mission was designed to do that. So we found tons of Earth-sized planets in their habitable zones, just not something like the sun, because, the sun is, the habitable zone is so far away that the transit probability is so low that we haven't been able to do it yet. Yeah, we found lots of planets in the habitable zone for M dwarfs, but M dwarfs, we don't know if they're going to be habitable because they're the flaring. Those stars are so active. So far, we've looked at a few with James Webb, and they just look like nothing's there, just rock. So it looks like they have, unfortunately, had their atmosphere blasted off, which is what we worried about. So it could be that most of those we found are not good for life, but we still are checking more. But the ones we checked so far have been bad news.
All right, I have one question of my own. With all the satellite constellations that are being put up there, I heard that SpaceX wants to put 1 million more satellites.
1 million more, yeah.
How much is that interfering with your work?
Me, nothing at all. If anything, I'm hoping it'll help it if it makes space cheaper. Okay. The reason we can do Starry, that mission, is because flight costs are so much lower now.
Okay.
Like for Starry, the launch cost of that is only 5% of the cost, which is kind of insane. Which means we should be doing a much bigger mission because, we should be doing a bigger spacecraft. So like it's lagging behind, but you could do a mission, 10 times that mass and it would still be 10% of the cost. So like we're anyway, we're still adapting as a field to that reality that used to be so limited by mass that you would make these tiny little CubeSats and you'd spend all this engineering to miniaturize everything, and you spend all this money because, of course, it was so expensive to make it bigger. And we're now moving to a regime that you should just make it bigger, make it faster, cheaper, because the launch costs are so much less, right? So it's like you could do them faster, you can do more off-the-shelf technology, save time, money. You just have to then give it all to SpaceX, but the launch, but I'm hoping they feel guilty too. Like I think if SpaceX could, maybe they feel guilty at some point and fund and actually directly fund some space astronomy. That would be a nice sort of consolation prize. If they ruin the night sky for ground-based observing, they might give us great space telescopes. But I'm still waiting to hear from Elon.
Team doesn't seem to be a strong point.
Yeah.
Thank you so much.
Thank you. Zoom.
All right, so that concludes our official meeting for the night. Of course, after astronomy, we like to enjoy gastronomy at the Redcoat Tavern, Woodward and 13 Mile. So we'll be headed there shortly. Hope to see as many of you there as we can. Have a good night and be safe, everybody.